two biconnected components of a graph can have option A at most one vertex in common, option B at least one vertex in common, option C no vertex in common, and option D exactly one vertex in common. What is biconnected component? A biconnected component is nothing but component of a graph which doesn't contain any articulation points. Articulation points are nothing but vertices, set of vertices which deletion upon which will disconnect the graph into two or more components. If you see option D, exactly one vertex in common, we can eliminate this option. Why? Because there are biconnected components of a graph which doesn't contain any common vertex, so we can eliminate this option, option D. If you see option C, no vertex in common, we can even eliminate this option also. Let us take one example. Let us take this as example. So here the biconnected components will be like A, C and CB. Here we have, here these two are biconnected components and C is the common vertex. So option C says that no vertex in common, so we can eliminate option C. Option B, at least one vertex in common. This is not true. Why? Because if option D is wrong, then option B is also wrong. Why? Because we can have biconnected components with no vertex, no common vertex, so we can eliminate option B also. Option B also, this is also wrong. Here option A is correct, at most one vertex in common. This is the correct option. We can have biconnected components with no common vertex, or even if you have common vertices, that should be only maximum of one vertex. We cannot have biconnected components with two common vertices. If two common vertices are common, then those two are not biconnected components. So here correct option is option A. Here the question is, two biconnected components of a graph can have option A at most one vertex in common, option B at least one vertex in common, option C no vertex in common, option D exactly one vertex in common. Here we can eliminate option D. Why? Because it is not necessary that each two biconnected components should have one vertex in common. They need not have any vertex in common. Biconnected component is nothing but the component in which there is the component of a graph in which there won't be any articulation points. Articulation point is nothing but a point which upon deletion upon which will disconnect the graph into two or more components. So here exactly one vertex in common is wrong. Why? Because we can have biconnected components of a graph with no vertex in common, so we can eliminate option D, no vertex in common. Option C, no vertex in common. We can even eliminate this option also. Why? Because we can have so let us take this. So this A, B, C. So we can say this is one biconnected component and this is one biconnected component. So BA and AC. So we can have one vertex in common. So we can eliminate option C. At least one vertex in common. So we can even eliminate this option also. We need not have one vertex. Just now we have seen. It is not necessary that we should have one vertex in common. We can have biconnected components with no vertex in common. And if we have more than one vertex in common, that means if two biconnected components have two vertices in common, then they are not biconnected components. So we can eliminate option B also. Here option C is the correct option. At most one vertex in common. Only maximum of one common vertex will be common in two biconnected components. So here correct option is option A. This question, program to calculate polynomial p of x is given, and in this program some two missing terms are there, and we have to identify those two missing terms. If you see the program here, int y is equal to an int I is equal to 1. This missing term we have to find, and while a greater than or equal to 0, we are assigning y is equal to 2. This is another missing term, and we are decrementing I. Here we are using variable I for counting purpose. So if we see the polynomial, it is a0 2. Here we have already initialized y to a0. Still we need a0 2 plus an minus 1, and so here we can say for termination condition, here one should be n minus 1, and while I greater than or equal to 0, y is equal to 2. This 2 should be ai plus, so it will come from the last. So here if n is equal to, we have assigned I as n minus 1. So this will be after this x. So ay, in order to generate this term, ai plus x into y. Here y we have declared as an. Y is nothing but an. First y is declared as, initially y is declared as an, and this I is n minus 1. This total thing will be y. After decreasing I value, we'll be getting n minus 2. Then y will become a n minus 2 plus x into y. Now y is this whole thing, which was a n minus 1 plus x into a n. So this will be y value. Now when we decrease now I will be n minus 3. So like that, recursively we can generate this polynomial. So here correct option is option B. First this here I should be initialized to n minus 1, and this y is here, this y should be ai plus xy. So here B is the correct option.